Well, good morning, and so just a copy from yesterday. When I was looking at it today in the morning, that made me think too many students thought the exam was too easy. Maybe. What do you think? Yeah, all right. Maybe it's not too many. But statistics gives us interesting data. For example, the ranking describes what you feel about problems. So 1 was easy, 2 was okay, 3 was hard. The larger number is, the harder problem is from your personal perspective. And from your personal perspective, the hardest problem was problem number 7. It has the largest ranking number. Now, there are actual numbers, like a grade. So if the problem is out of 6, and the grade, average grade is like 5.2, so 5.2 over 6, that gives the actual ranking, the actual difficulty. And the larger this number is, the easier the problem, the higher grade. And it turns out the same problem which you think was the hardest actually was the easiest. So don't really rely on your feelings, they lie. Well, we're solving problems on work, energy, and this is one of the typical problems. So we've been pushing a box. You saw the box, and well, it doesn't have to be a box. It can be anything. And in this situation, I assume it moves faster and faster, and we need to calculate how fast it's moving after we pushed it for 2 meters, right? So we know everything we need to use distance. Why is it so thick today? No. 2 meters. Mass, 4 kilograms. Now, we've learned 2 equations. One we call work kinetic energy theorem. So let's use this one. It says change in the kinetic energy, and that's one other symbol, just a K, kinetic, should be equal to the work. But if I leave it like that, that technically is a mistake, not any kind of a work, a specific net work. So mv squared over 2 final minus mv squared over 2 initial should be equal to, well, again, each force acting on an object in general might do a work, positive or negative or zero. We have force of gravity. What's happening today? mg, we have normal force, frictional force, and the applied force, and the angle, this or that, is 60 degrees. So theoretically we should add 4 numbers: work done by gravity, work done by normal force, work done by applied force, work done by friction, as we know from yesterday. some of these terms actually are zeros. Yeah? For example, do you tell me? Gravity and normal are zeros because those are perpendicular to the displacement. Now, work done by applied force. It's a constant force. We can apply equation, magnitude of a force, magnitude of the displacement, cosine of the angle, and work done by friction. We know it's negative. That's cosine of 180 times, well, let's write friction times displacement. So what does this give us? 14 times 2 times, well, again, we need to see an angle between two directions. That's displacement, that's applied force, that's the angle we should use. We have to draw each arrow from the same point, and this is 60. And now it's minus frictional force, as we know. Let's write it here. Related to normal force. And normal force in this situation, as we know, equal to mg. And we need to remember that work and force, different words, they represent different physical quantities. A force is a vector, represents an action. A work is a number, represents how much energy is being spent on something. So force of gravity is not equal to 0. It is equal to 4 times 10, 40 newtons. So that's also going to be 40 newtons. But work done by gravity is 0. So force is not 0, but the work is 0 in this situation. So, and friction will be equal to coefficient, which is 0.4. I can read it here on the screen. And the normal force is equal to mg40, and the distance is 2. So, because the motion starts from rest, there is no initial velocity, so we should write 4 times final speed squared divided by 2 is equal to 14 minus, what is it, 4 times 4. Uh, 16 times 232. Did I miss anything? It should be positive in my mind.
Where are you getting 14?
Hmm?
How do you use it 14? Plus 14 minus 10.
This cosine of 60 is a half. 14 times 2 divided by 2, that should be 14. Let us make a coefficient smaller, 0.4. 0.4. So that's going to be 3.2, right? I have a designated computer. So 3.2, the last term.
For friction, yeah.
And so 14 minus 3.2 11.2. 10.8. Yeah, 10.8. 10.8. And so speed will be equal to square root of 2 times 10.8 over 4. That's about square root of 5, 2 point something, 2 point whatever, 2 point what, 2.2? Okay. So this illustration combines, yes? Cannot hear you.
Where did the -1 come from?
-1. Just a second. Again, to refresh what we know about friction. If we pull or push an object, so displacement, velocity, they point, let's say, to the right. Force of friction always opposes. So if we want to calculate the work done by friction, it should be equal to magnitude of friction times magnitude of the displacement times cosine of the angle. And the angle has to be measured between two vectors which point opposite to each other. That's where the minus is coming from. Negative. Friction always does negative work. Does it mean friction is always bad? No. Without friction, we couldn't walk, we couldn't drive. We would just be moving feet without actually propelling ahead, because friction makes us move ahead. So, negative not always means bad. Yeah. All right. So, question is, as we said, law of conservation of mechanical energy, or master equation, and work kinetic energy theorem. It's the same equation, just terms are rearranged. It's like looking at two photographs of the same person. When do we choose one? When do we choose another one? Well, there is no special rule, but statistics shows that when the problem doesn't involve any friction, usually it's easier, kind of simpler to see what's happening if we use the law of conservation of mechanical energy. But when friction is involved, in that case, like we just did, it turns out kind of easier to process the problem using work kinetic energy theorem. But again, it is completely up to you. Please tell me what you think about this question. In this situation, the same block, the same object, let's say like this, now slides on the incline. Horizontally, let's say we pushed it, when it just slides on its own, there's gravity, normal, and friction. Right now, there's gravity, normal, might be static friction in my finger, but if I let it go, there's only gravity, normal, and friction. That's it, only three forces. For each force out of these three, of course, we can calculate work. And this question about work done by the normal force. Right? Yes. But also, you should think about work done by gravity, work done by friction, if it's there. So, first of all, I need to check. I haven't checked yet. So let's check. Today. is day 10. Question 2. Question 2. And the most popular answer is number 1. Well, so this is what I want everyone to do. Time finally came from that, for that. I want to draw you a picture. I want to show 2 locations of the box, the initial and in a second. Then I want to show you very clearly the vector which represents displacement. Then I want to show you that you show the angle and take a photograph of that picture and email it to me. I don't believe that you don't have smartphone on you. I just refuse believing that. So you have it, and it means you can take a picture of anything. So, but I need you to take the picture of your diagram with all elements, Yeah, I just named initial position, a position of the box in a second, displacement, the angle between normal force and displacement. So take a picture, email it to me, please. And this is a time when I want to rearrange this. Now becomes question number 3. After you send me a picture, please enter the answer to the same question, but now in the third place. Question number 3. So again, initial location is here. It slides down. So you should draw the new location in a second or a half of a second. You should draw a vector which represents the displacement. You should show the angle between the normal force and the displacement. Take a picture. Re-enter your answer. Now it's question number 3. All right. So far, no pictures. Only bills. And don't worry, it's not going to be graded. It's for statistical purposes. I'm going to usually when I collect all the pictures, next day I give some comments which will help for the future. All right. Starting getting pictures. So you send the picture, and after that you should again go to Webassign. Now this is question number 3, and enter your answer. You can enter the same answer as before. You don't know if it's right or wrong. I didn't say anything. Yes? Oh, you still don't know? That's a good question, of course. This is also the most reliable way to take attendance. So let's see what is happening on a Webassign. I do see the change in the distribution. Again, I'm not saying anything so far, but you can see that distribution has changed. Before you did all that work, most people chose answer number 1. After, most people chose answer number 2. What does it prove? What does it say? What conclusion can we make from this experiment? This is an experiment. And conclusion is what? What do you think? Picture helps. So if you try and solve a problem and you don't draw a picture, you don't like yourself. I don't know why. Because it helps, and you don't want to help yourself. Well, of course, initial position, let's say in a second, it will be here. That will be the displacement. That will be the angle, which is 90 degrees. Displacement, angle, the work done by normal force supposed to be equal to normal force times the magnitude of the displacement times cosine of 90 degrees. That's 0. But normal force doesn't always do 0 work. If you are in an elevator, normal force actually move you up and down. So, but when normal force is perpendicular to the displacement, it doesn't do any work. What about gravity? Does gravity do work in this situation? Yes. As long as height changes, gravity does work. So what do we do about work done by gravity? This, we need y-axis. This is y initial. If it slides down, this is y final. That's all we need. The work done by force of gravity is equal to m times g times y initial minus y final. In this situation, when the box slides down, what kind of work does gravity do? Positive or negative? What do you think? Think. You have to stick to your reasoning. You don't have to change your mind only because someone tries to scare you. Of course, this is greater than that. The difference is positive. The work done by gravity is positive. So what does it say? Don't judge the book by the cover. When many people start judging book by cover, we get Trump. So that's a very serious matter. What about work done by friction? Positive, negative? Always negative. You shouldn't even think about it, because work done by friction is always negative. Well, so these are all equations. Right now, you should print out the equation sheet number 2 and start using those equations when you solve problems, when you do the labs. A block slides down, calculate the final speed. Okay. Nothing new. Well, this is the initial height. This is the final height. And what is, if we set 0 at the bottom of the ramp, and that's normally the best choice, choose 0 at the lowest location. So the y final will be 0. Y initial is equal to, please tell me the number. What? No? Yeah, here. It slides from here to here. This is a picture in the middle. 3, exactly. This is a 3, 4, 5 ramp. This side is equal to 4. Why this side, this one? Why this side can't be 5? Why? It's shorter. So the longest should be equal to 5. So that's 3. That's it. Now, the initial speed is 0, and mv squared over 2 minus kinetic initial should be equal to what? Work done by gravity, work done by friction. Technically, I should write work done by normal force, but we just said a minute ago that's going to be 0. So work done by gravity. We just said a minute ago it should be mg. Work done by friction should be negative. Well, let's call it L. Yeah. In this equation, M10 3 minus 0 minus 0.5 the small length. I needed to write an expression for the normal force. This action has nothing to do with what we learned today or we learned yesterday. This action is related to what we learned before about forces, right? So, if I write just mg, would it be correct? No. We know that the normal force and the force of gravity are related, and the relationship is also given by the angle. So that's the normal force, that's force of gravity, 90 degrees. Normal force equals mg cosine theta. Now we arrived at a very important point. People make mistakes very often because the equation for the work has the angle which we call theta. And this equation is not for work. This is for normal force. And this is the angle we also call theta. And when people use the same letter, they confuse these angles and make mistakes. So what do we do? Well, some people use different variables, different letters. Some people use some kind of an indication to demonstrate it's a different variable, it's not the same. But there is one variable which still remains unknown. M. What does it mean? Meter? No, mass. And what do we do about it? What do you think? First, we should believe in the universe. We should believe that the problem is solvable. And we should act like we know what this variable is equal to. And hope that it will be cancelled. And it will be cancelled. So, that's what you call factoring out, right? So first we need to simplify equation. mv squared over 2 should be equal to m times 30 minus m times 1.5, 10 cosine of theta. Cosine of theta actually is just 4/5. We don't really need this angle. All we need is the cosine of that angle, and cosine equal to side adjacent to the angle over hypotenuse, and that's 4/5, 4/5 times distance traveled. So from the top to the bottom, distance traveled by the block equals what number? 5. That's the length of this ramp. Well, so which equals to m. We use it as a common factor. 30 minus, so 5 and 5 cancelled. 0.25 times 10 is 0.5. 0.5 times 4 is a half of 4/2. So m times 28. And now we can see, yes, it is getting cancelled. It's a common factor on both sides. So speed will be equal to square root of 2 times 28. Square root of 56. 7 times 7, 49. So 7 times 7 point what? 7.48. 7.5. Okay. Any questions? So you see, it's all about believing. An opposite problem. Now we want to push it. And what might happen? Well, if we don't give the initial speed high enough, it stops and then slides down. So there is, if we push it too fast, it can fly away, fall off the ramp. So there is that critical speed which we need to give to this box in order for the box to reach the top. Yes?
How did we determine which side was coming for? I know the hypotenuse was that. Did it say? Okay, so there it was.
Yes. And now we use exactly the same ramp. So 4, 3, 5 theta. But now we pushed it like this. That's the initial velocity. So that critical speed we give to it means that it stops at the very top. Not before, not flies away. It stops at the very top of the ramp. But, well, gravity, velocity. How does friction point now? Opposite to velocity. So friction, in this problem, friction points up the ramp, and the work done by friction is negative. But now we switch the direction of the friction. Now it points down the ramp. So that means the work of friction is positive. Yes or no? No. Friction always does negative work. But gravity does, well, work which depends on the initial and final locations. Again, the initial speed minus 0 should be equal to normal gravity friction. Now, still 0. Sorry. Final minus initial. Final is 0, initial is not 0, final minus initial. Now it's going to be equal to m. Why is it thick again? Times 10 times. That should be initial minus final, always initial minus final, so 0 minus 3 plus friction does negative work, coefficient of friction, normal force, what should I write for the cosine? Does it make any difference if the box slides up or down when we write the normal force? No? Does it make any difference? It doesn't matter how it slides. Only angle matters. So same. Now it's too thin. I don't know what's happening. And distance again is 5. Now, if you look at this equation, for the box sliding down, and at this equation for the box sliding up, do you see the difference? Is there any difference? This is for the box sliding down. This is for the box sliding up. Do you see a difference? Is there any difference? What do you think? Exactly. Absolutely right. There is no difference for work done by friction, but the work done by gravity, of course, is different because it depends on how the object is moving. If it's moving up, the gravity does negative work. If it's moving down, the gravity does a positive work. So you may have thought that we should get exactly the same answer for the speed, but no. Turns out it shouldn't because the gravity switches. But still, we can cancel m. So still, speed squared, well, okay, mv squared over 2 should be equal to this. And inside, we should write 30 plus 2. So this minus, and this minus, and this m, and this m, just common factors. And now v will be equal to square root of 64. Which is? Here we don't even need a calculator. But again, mass is not, well, actually here it's even given, but we didn't use it. So sometimes when you may think something is missing, just power through the problem. Treat a variable like a known. There is another hint which sometimes just helps to get the final number. Technically, it's not the correct approach, but it helps if you don't know what to do. If there's a variable like mass, which you think maybe needed, but not given. Maybe it's not important. Maybe the value of that variable not important. And if the value of the variable not important, that means it can be any value. So in that case, you can assign some convenient number, like 10, and see if it helps you. Yeah, that's like a workaround if you don't know what to do algebraically. Well, one more example. We have solved this problem, well, similar projectile motion, and we know what to do. We could have used all our equations, velocity equation, position equation for x and y components. But now we can solve this problem faster using law of conservation of mechanical energy. So here I used work kinetic energy theorem because of friction. Here we neglect any air friction, and if there is no friction, I always use the law of conservation of mechanical energy. So what do we do to use that law? Well, the law says initial mechanical energy has to be equal to the final mechanical energy because there is no freaking friction. And what is mechanical energy? Mechanical energy, by definition, is just the sum of kinetic energy and potential energy. In our case, it is a gravitational potential energy. What is kinetic energy? Kinetic energy is equal to mv squared over 2. What is gravitational potential energy? It's mgy. So we just write these numbers twice, these expressions twice. And if I look at this equation right now, I can say something about the mass. What can we do to it? We can cross it out. Because as we solved a similar problem in the past for the ball, we didn't have to know the mass. So it shouldn't be important, and it's not, it's getting canceled. Now, what do we do? Well, we gotta set the origin, and now we can start writing numbers. 38 squared over 2 plus 10 times initial, which is 70, should be equal to the speed we are looking for over 2 plus 10 times 35. That's it. And now you can finish. It's a very simple mathematical calculation. So you see, we could have done it using all that projectile motion stuff, but sometimes using energy approach gives solution faster. The answer is 46, actually. This is what the problem is about. On my back. This is a 4 kilograms, 9 pounds. So this is what I'm going to do with this. That's it. One more time. This is an experiment. What is happening in terms of energy? Well, first of all, if I need to lift it, I have to do work. My hand does work. That work is positive. I'm transferring the energy which I got in the morning from coffee into this weight. But gravity does negative work. Gravity always does negative work when object moving against gravity. So the more work I do, the more energy I pump in this, the higher it gets, the more potential energy it has, gravitational potential energy. So if I let it go, that object starts moving faster and faster. What's happening with that? Gravitational potential energy starts. I just love it. Gravitational potential energy starts transferring into kinetic energy. It's moving faster and faster. So here, when it crashes this can, let's try a big one. Still works. Do you think mechanical energy is conserved? And the answer is no, it's not. It's almost conserved, but what is the reason for mechanical energy to change? The law of conservation of mechanical energy in general has a term which is negative. So as long as we have parts touching each other, moving parts touching each other, there's friction. As long as we have friction, mechanical energy changes. But what about energy in general? That's not a question to you. Energy in general always conserved. So this is a difference between words. Mechanical energy and just energy. There are many different forms of energy, just electrical, magnetic, etc., etc. So when we say mechanical energy, we mean kinetic plus potential, that's it. When we say energy, that might involve many, many different forms of energy, and energy is always conserved. We only can transfer energy. We can store it, transfer, release it, but the total amount of energy in the isolated system always remains the same. Except we have no idea where did energy come from at the beginning, at the Big Bang. We don't know. Well, why energy is so important? Well, we can't live without energy. For example, the energy we use basically comes from nuclear reactions on the sun. Light brings that energy to plants. We eat plants, animals eat plants, we eat animals. We burn that energy. We do some work, we get sweaty, we get fat. And every year we consume more and more energy. The world in general needs every year much more energy than the year before. And where do we get that energy from? Unfortunately, most of the energy so far comes from coal and oil. And as we know, it's, well, we doesn't include certain people, but as we know, it's bad. It's bad for the planet. So we got to do something about it, and the point is using, even if it's dangerous, but using nuclear or thermonuclear energy is inevitable eventually. Now, next question. Actually, you don't know yet what the question is about, so don't enter anything. And I forgot to mention, but you know that this is not question 3 anymore. Yeah. Numbering has been changed. Now, what do I want to do? That's what I want to do. This, what the question is about. I have here two tracks. One is, we call path 1. Second, with the deep, we call path 2. I have two chords. Okay, almost frictionless. And I let them go simultaneously at the same time. So theoretically, we have three possible options. Yeah? They reach the finish at the same time, or the green, the first one wins, or the red, the second one wins. And the question is, what do you think? So which will reach the finish first? That's not going to be a tie, so you should choose one if you think this card finishes first, wins the race, or two if you think this. And after you enter your selection, you can compare, right? What do you think? Number one. What do you think?
Said one, but I regretted it after I put it in.
It happens. How many people say one? Please raise your hand. How many people say two? Two. Have you seen it before? There are many videos. Well, basically every demonstration you see here you can find online. Yeah, of course. What does it prove? Well, only one important fact, that energy and time not related. It could have been different. Let's imagine that this actually is very, very deep, so it's just very, very long, so long that the green card reaches the finish before this even reaches the bottom. Yeah? Still, it tells us that we cannot relate directly energy and time. Why? Energy. What do I do? This is what I want to do. Why do we talk about energy? Because they begin from the same height, they begin from rest, and they end at the same height. So the energy conservation says that mv final squared over 2, well, minus 0 should be equal to mg y initial minus y final, neglecting friction. That should be the same for both. The same. So the final speed actually should be the same for both. But time is different. But again, if you look at the second track, it's longer. So we would expect from our intuition, longer path requires more time. Turns out, not the case in this case. So again, don't always follow your feelings. Do the math. This is what we've studied up to now. Everything about energy, work. This is what we need to do. And we've seen this equation. That's about linear momentum. And I want to start from a question again. What do you think? We've solved a very similar problem. It's about a ball bouncing off a wall. It doesn't have to be a wall. Yeah. When an object bounces off a surface, it means there's a force acting well, there is a force acting from a ball on a wall. There is a force acting from the wall on the ball. That's why it reverses its direction. So in general, we know that, well, if you play tennis, you can spin the ball. It might spin, and it might be flying, well, making some complicated trajectory. We neglect everything. We neglect everything except the wall acting on the ball during that, well, we call it a collision. A collision usually when two objects touch each other for a brief moment of time, very briefly. So, and here, please, this is a picture which we call before the collision. This is the same wall. I want to draw a picture immediately after the collision. This is the same wall. This is the same ball. How should I draw the velocity now? Opposite. Now, final. What number should I write for the magnitude of this velocity now? Same. That's what this word ideal means. In reality, of course, it could have been different due to friction or something else. But ideal means it just bounces back. So now what do? We want to calculate acceleration, right? Well, acceleration equals, we know, delta v over delta t. But we need to keep in mind that these variables, not numbers, they are what? Vectors. That's it. If we remember that fact, it's very important. We know what to do. Again, we've done it before, and we still have to keep it in our memory. If we want to calculate the acceleration, time, given 0.01. What number should I write Okay, first, that should be final x minus initial x. What number should I write here? What do you say? What do you say? What number should I write here? Here. -10. And I know I've seen people forget it. And when they forget it, they get 10 minus 10, 0, which doesn't make sense. It cannot be 0. So again, this is a very important moment. Components, vectors, not numbers. But if we keep in mind the difference between numbers and vectors, so 10 minus -10, that gives 20 over 0.01, 2000. Mass times acceleration gives the force, so we can calculate the force. $100 grams, can we use grams? No, convert into kilograms. Uh, 200 newtons. Now, how do we use this? Well, basically what we did is we used the Newton's law. V final minus V initial times time. But because this phenomenon, a collision, happens very often, there is a simpler way to analyze that phenomenon. And to do that, first of all, because we don't like fractions, we multiply everything by time, the time of the collision. And secondly, we give a name to everything we see now and a special symbol. This product has a name, the impulse of a force. This product has a name, a linear momentum. And now what we have is an equation which relates these, a short equation which relates these variables. This is a Newton's second law in disguise. The impulse of the force equals change in a linear momentum. And of course, I got a slide. We have a name for this equation, impulse momentum theorem, IMT. So if you see in the lab IMT, that's what it means, impulse momentum theorem. How do we use it? Well, sometimes this equation becomes very convenient when we need to understand what's happening to the object. So we rewrite this law. If we know the initial momentum and we can calculate or measure the impulse, that gives the final momentum. And there is another situation when, by some reason, this term is zero or very small. One of the situations is collision. If it happens over a fraction of a second, that delta t, that's time, is so small that even if the force is strong, sometimes we can neglect the value of j. In that case, this is zero, which means the linear momentum doesn't change. The linear momentum of what? Of wherever it is. It's a system. It can be this object. It can be something else. It will be two cars colliding with each other. But so far, we talk about impulse. If the force remains constant, to calculate the impulse using this equation, we have to multiply force times time. On the graph, if the force is constant, on the graph, this product is equal to the area. Yeah? It's a rectangle. This side represents the force. This side represents time. This height times base, area. But now we make a transition. We make a so-called generalization. We say that even if the force changes, the impulse the force transfers to an object, the impulse still will be equal to the area covered by the graph of the force as a function of time. How can we prove it? Well, that's what every scientist does. Scientist pretends that this is not a smooth curve, but actually a combination of many, many very thin rectangles. Basically, that's it. And for each rectangle, we can use this equation, calculate area, and then we just add them up. In mathematics, we call it an integral. Yeah. But here, for us, it's just area. As long as we can measure that area, and we always can, one way or another, we always can calculate this variable, the impulse of the force, during that period of time it was acting. If we know impulse and initial momentum, again, well, now we can say this area. An example. Let's say we have a graph. A force changes in time differently. All we have to do now is just apply straightforwardly everything we just said. And the graph gives all the numbers. So what do we need to do? Just read the numbers So P final should be equal to P initial plus area. All right. Is equal to a linear momentum by definition is equal to the product times velocity. Well, hence, first. So this axis represents time. This graph represents how force changes with time. But it's about object traveling in space. So at a certain instant, it's been somewhere, we don't know where, but we know that initially it was traveling to the left. Why is that important? It says something very important about the initial velocity. Yeah, so it should be equal to the magnitude of the initial velocity is equal to 4 meters per second, but the initial velocity, the actual value component, is negative. Again, people sometimes forget to check the directions. Now we all set 3 kilograms. So 3 times velocity final, that's what we're looking for, should be equal to 3 times negative 4 plus the area. How do we calculate area? Well, it depends on the shape. Yeah. At first we see a trapezoid, then a rectangle, then a triangle, and then another triangle. That's it. We just break it down in smaller parts and calculate the area. And I thought I had a slide when it's been done already. All right. Trapezoid 1/2 times numbers 3 and 6 bases 3 plus 6 times, and the height for this trapezoid is like this. You should imagine a standard trapezoid actually would look differently if you turn it by 90 degrees. So 4 plus next area. Next area comes from 4 to 9. So rectangle 9 minus 4. Times 4 height. Plus first little triangle, so the base is 10 minus 9, the height is 4. 10 minus 9 times 4, and that's over 2. Plus, and that's the only tricky part. Because in this situation, when we say area, we actually don't mean the magnitude. Yeah, we have to use actual numbers, actual values. So, and these values are -8 and here. So 1/2 of -8 times, and of course the base, the difference 12 minus 10. 12 minus 10. And I'm not going to calculate, you can finish it at home. I just need to erase this. I don't know what this is. That's it. Now, 3 plus 6. Sometimes when I switch back and forth, okay, now I think everything is correct. No, that's it. Cool, not a little. That's what we do when we need to calculate the impulse and relate it to momentum or velocity. Question, again, wherever it is now. You don't know the, yes?
Can I ask a quick question?
Yep.
I didn't catch what you did. So the one triangle that's below 0, are we getting like the total area or the positive area? Like are we adding that triangle or subtracting it?
We are adding area, which turns out for this triangle is negative. We just literally use numbers we read here. So it's not kind of geometrical area, it's a physical area, which sometimes can be negative. And the rule is actually simple. Above the axis, positive. Below the axis, negative. Here, it means that the force was pulling or pushing to the right, and here it means the force changed its direction and starts pulling or pushing to the left. That's it. Did I answer? Okay. So you don't know what these words mean, so this is what is happening. Two balls, identical, but they behave differently. It's just because they've been manufactured from different material, and this bounces back, and this is not. And the experiment is kind of neat. What you see? Well, okay. I've got this wooden block, and this ball actually we call sad because it can bounce. It's not strong enough. This one is happy. It is strong enough. So the question, which of these balls exerted stronger force? And so I'm just switching back. My brain works faster than this thing. So you've, yes? Yes? The only difference is the property of bouncing or not bouncing. Actually, I have that's what I have. Little piggy. It doesn't go to market. You don't let it. We keep it here. It suffers. But you can buy it and play it at home. It doesn't bounce, no matter what. No matter what you do. So this is the analogy of this sad ball. See? That's why if you don't have a strong force in you, you're always sad. But naturally, this is not a tricky question. Obviously, the ball which knocks it down exerts the force stronger than the ball which doesn't. The question is, well, how do we describe it mathematically? Now we know how. This is how. Well, let me write it. What do we do to get the force? We treat momenta as vectors. And the difference is, for the sad ball, the final momentum is practically zero. It doesn't bounce back. But for the happy ball, the final momentum is not zero. And we have solved this problem before with numbers. Now, that solution remains correct for the happy ball. When the object is bounced back, so the final momentum is not zero. When the object doesn't bounce back, the final momentum is zero. So in this situation, the force exerted on the ball or by the ball is actually doubled relative to this situation. And how do we use this? Well, there are many, many applications. For example, soon, relatively soon, we're going to talk about gases. And each molecule acts like a happy ball. It hits the wall, it hits the surface, and bounces back. So if we know how to calculate the force acting from a single ball, from a single molecule, we just multiply by the number of molecules, and we get the force acting on the wall. Force over area is pressure. We can calculate the pressure gas exerts on anything. This is maybe a future of traveling, space traveling. It's a solar sail. If it's really, really large, light actually exerts a strong pressure on it, because light also can be seen as many, many tiny particles, photons. And if you want to make a solar sail, would you make it shiny or would you make it black? If you make it black, that's what would have been happening. Light would have been absorbed. So you won't make it shiny. The light would be bounced back. And that would exert twice more force. So twice higher acceleration. Now, as I said, for collisions, one of the reasons, there's also Newton's third law, I'm not going to talk about it, but one of the reasons that we can apply all this theory for collisions is that collision usually happening very quickly. And when collision is happening very quickly, the linear momentum of a system remains the same. And that's all I want to say about it. Well, thank you. We'll pick it up tomorrow from this. Don't forget, there's lab today and tomorrow. Same room. Morning. Just a sec. So let me first. No, first I have to do this. Just give me a sec. I need to. Yes.
So not next Monday, but the following Monday, I have orientation for like my